prioritizing CVEs isn't just about CVSS scores. The same vulnerability gets ranked completely differently depending on whether your security team is currently prioritizing active exploits, patch availability, or general severity. Standard LLM triage systems fail here because they assume a fixed, explicitly stated scoring criterion. Enter HARP, a graph-grounded, preference-adaptive ranking framework that learns to prioritize without ever requiring a written preference prompt. Here's the architecture. HARP retrieves candidate CVEs from a structured vulnerability knowledge graph and generates a shared feature summary. Instead of relying on a single monolithic scorer, it attaches lightweight, policy-conditioned adapters to a frozen LLM backbone. These adapters implement three distinct prioritization views: global risk, enterprise exposure, and end-user impact. For any given query, the system selects the optimal policy per view by computing embedding similarity between the query embedding and each policy's key vector. The real innovation is in the fusion stage. Raw view scores are z-score normalized within each candidate, set to prevent numerical scale dominance. Then HARP leverages a support bank, a curated collection of historical labeled triage cases from your current operational scenario. At inference, it samples a few of these supports, fits a three-dimensional weight vector across the views by minimizing a ranking loss, and blends this adaptive fusion with a uniform multi-view regularization term. This regularization is critical. It prevents the fitted weights from collapsing to zero or negative values, ensuring complementary evidence from all views is preserved. Finally, a lightweight top-K consensus rule preserves cross-view agreement on the highest priority candidates. Crucially, the adapters are trained using sequence generation loss to align with normalized score outputs, but the actual preference adaptation happens entirely at inference time through the support bank. There are no scenario tokens, no explicit prompts, and no intermediate scenario prediction. Tested across three distinct preference scenarios and multiple backbone models, HARP consistently outperforms fixed baselines, RAG variants, and single-view prompting. It demonstrates that preference-aware vulnerability management is achievable through structured evidence, modular parameter-efficient adaptation, and historical ranking supervision.